In this video, we're going to be learning about the kinetic molecular theory for gases. The kinetic molecular theory for gases is the simplest model for describing how gases behave down at the molecular level. Theories in science are the most powerful type of explanation. And so in this theory, we're going to go through 5 different postulates to talk about how gases move around on the particular level. So here's a sample of gas, and you can see these gas particles, and then these trails behind them are trying to show like what direction they're moving in. So that one's moving in that direction, and so on. When we talk about gas particles, we could either be talking about gas atoms, like individual atoms, or gas molecules, meaning little, whoa, what happened there? Little clusters of atoms. So we could either have molecules or atoms of gas. And so just to have a generic term, we're going to call them particles. So for our first postulate of the kinetic molecular theory, abbreviated KMT, gases are composed of molecules or particles that are in continuous motion, traveling in straight lines, and they do not change direction until they collide with one another or they bump into the sidewalls of the container. And so here we go. These are moving in straight lines. What we do not want to happen is for the gas particles to change direction. So this is against the kinetic molecular theory of gases, where this one's just randomly trying to change direction and go in a curvy path. And so in kinetic molecular theory of gases, there will be none of this. There will be no change in direction or going in curved paths. When we talk about gas particles moving around in straight lines, here's a kind of 3D representation of gas particle movement. We have a gas particle here, and then it bumps into the sidewall of the container, and then it goes flying off this way, and then bumps into something, and then it keeps bouncing. And so you can see all these paths here are straight. And so the mean free path is the distance it travels before colliding with another gas molecule. The word mean here does not mean like angry or not friendly. It means average. And so when we talk about mean free path, we're talking about average path length between bumps between molecules. That's known as a mean free path. The second postulate of the kinetic molecular theory of gases is that the particles themselves take up so little volume compared to the volume of the container that we can pretty much just ignore the volume of the particles themselves. So here in this picture, you can see that the container is mostly empty space. So like all this black stuff is just empty space, and the gas particles indicated by the purple dots are very tiny, and so the percentage of space occupied by the gas molecules is very, very, very small. What's against the kinetic molecular theory of gases is for those gas molecules to occupy the majority of the space. And so just to give you an idea of how much empty space there really is, at STP, argon atoms occupy only 0.01% of the gas volume. And so if we kind of scaled this up macro size, then an argon atom, being the size of a golf ball, its closest neighbor would be like 4 feet away. So it's like they're socially distancing. The third postulate of the kinetic molecular theory of gases is that the pressure exerted on the sidewall of the container is the result of collisions of the gas molecules with the sidewall of the container. And we kind of mentioned this earlier, and that's because it is one of the postulates. And so when we were defining pressure, we showed this picture. We said that pressure is equal to force over area. And because these gas particles are always moving constantly, then the sidewall of the container is being hit very, very frequently. So it's essentially like it's a constant force on the sidewall of the container. It's just that force is being applied by different gas particles. The fourth postulate of the kinetic molecular theory of gases is that all collisions are completely elastic. Now, this word elastic is a physics term, and the opposite of elastic is inelastic. The formal definition of elastic collision is that the total kinetic energy before and after the collision remains the same. And then in an inelastic collision, some of that kinetic energy is changed into heat or lost into heat. So we do not have inelastic collisions. Let's explain this elastic collisions a little bit more. Like, let's pretend that all of these were like really super bouncy balls, or in this case, they're billiard balls. Billiard balls, when they collide into one another, they bounce right off each other. These are like balls of Play-Doh. Because Play-Doh is soft, if you're going to throw balls of Play-Doh together, then they go kind of splish, and then they deform, and then they don't bounce as well off of each other. Billiard balls do bounce off of each other very well. And super bouncy balls also bounce off of each other very well. The fifth and final postulate of the kinetic molecular theory of gases is that the average kinetic energy of a gas is directly proportional to the temperature in Kelvin. And so here is a graph showing the molecular velocity and how many particles are at that velocity. So it's kind of like a histogram here. And then you can see that there's different temperatures. And so as we increase the temperature, on average, the particles are moving faster. And since kinetic energy is 1/2 times the mass times the velocity squared, then having more particles at a higher velocity means that you are higher energy. I did want to point out, though, that not all of the particles are moving at the same speed. There is a distribution, and it's not a symmetrical distribution either. More on that later. So this kinetic molecular theory of gases is a very powerful scientific explanation that can be applied to all of those simple gas laws, like Boyle's law. Boyle's law had our PV is equal to PV relationship. And so Boyle's law says that as the volume of gas is inversely proportional to pressure, and so if we decrease the volume going from this picture to that picture, then we are making our molecules collide with the sidewall of the container more. And that will increase the pressure because we are having more collisions with the sidewall. And that's consistent with our kinetic molecular theory of gases and the origin of that pressure. Then we also have Charles's law, which is the relationship between volume and temperature. And so according to Charles's law, if we increase the temperature, then we're going to be increasing the volume. And so if we are trying to keep this at constant pressure, increasing the temperature will increase the force of the collisions against the sidewall. However, if we increase the area over which those collisions are occurring, then we can maintain that constant pressure, because remember that pressure is equal to force over area. And so volume increases, and that's going to increase our A, and that's going to make our pressure smaller. And then T is going to increase force. So And so since both of these increase, then we can maintain constant pressure. Avogadro's law is that relationship between volume and moles of gas. And so we have our V1, N1, V2, N2 relationship. And as we increase the number of moles, then that's going to cause the number of collisions to increase, but we're trying to maintain a constant pressure. And so to maintain that constant pressure, if we are increasing the number of collisions, we have to increase the area in which those are occurring so that it spreads them out more, and therefore our pressure is maintained. So we're spreading out the collisions so that they aren't happening as close together, and that way we can keep pressure constant. Kinetic molecular theory also explains Dalton's law of partial pressures. And so according to the kinetic molecular theory, the particles have negligible size and they do not interact with one another. So that means they don't have attractive forces or repulsive forces. They have to travel in straight lines. And so particles of different masses have the same kinetic energy at different temperatures. And if kinetic energy is the same, the total pressures of the collisions is the same. And so all of these postulates of the kinetic molecular theory really lead us back to that PV is equal to nRT relationship between our different gas properties. And theories are used in science to explain laws. And so all those simple gas laws, they just tell us the relationship. Theories explain what that is, why that is. So laws don't attempt to explain anything. Theories explain things. Theories have models, and they help us understand the world around us. Now, there are cases where the kinetic molecular theory of gases does kind of break down, but understanding the conditions in which we do observe deviations from the kinetic molecular theory helps us better understand gases themselves. And so it's a very powerful way of envisioning, modeling gas behavior in your head.